Last talk before the coffee break will be given by Valery Smyshlyaev on homogenization of resonators by a two-scale transform and generalizations. We hope that this won't happen too often. Please.
Scared to come to get any close to that. Thank you, Malte. Thanks to the organizers. Honor to be here, which I'm not sure I have deserved for my relations to Wiener-Hopf. Scratching my head how to try to fit to the workshop by association. So Wiener-Hopf and this sort of techniques are about transforms, right? Fourier transform. You do first Fourier transform, right? It's my justification. Yeah. So I guess I'll try to emphasize this part of a project we've been pursuing for some while with my colleagues Ilya Kamotsky and Shane Cooper in UCL, right? So essentially, the other keywords resonating with earlier talks today, kind of homogenization process in the presence of resonators. Sasha had some of such keywords in slightly different context. Point here is that this kind of interesting phenomena, kind of a band gap opening, and for particular Scanian regimes, there's a subtle asymptotic analysis for, in this case, high contrast heterogeneous medium, and the word homogenization itself is a bit misleading because the asymptotic behavior remains intrinsically to scale, right? It's not fully averaged, right? And the presence of the micro scale exactly reflects the physical effect of the resonators, but homogenization techniques are still relevant because of that particular scenario, right? And if you need to do it honestly, then what you develop is a kind of a combination of scaled Floquet-Bloch transform and scaled inverse Fourier transform, right? Essentially, a combination of those could be called a two-scale transform. In fact, we called it two-scaled interpolation operator until we discovered that, as often happens, right? Someone developed similar tools before, but for us, one of that they serve the purpose in one way or another. So after this little introduction, here is the plan for today as a part of motivation, the effects, right? Microresonance is how they enter the high contrast homogenization for a basic model. And then I will try and emphasize in the middle, right, central part of my presentation, how this transforms methods help to succeed in describing this two-scale limit behavior and controlling everything, including the errors. And in fact, when you do it, you discover that you really rely on quite a few basic principles, and there is no need to stick to this basic model, so you can expand it, and there is, as a result, quite a broad set of examples can be covered essentially by repeating the same key steps, creatively adjusting them. So here is self-advertising attempt, right? Actually, that's currently in public domain, preprint a few months ago already uploaded. Actually, I have now 73 pages. It's not try compressing it, so we'll keep on growing, trying to focus a little bit. But those interested already have something available in public domain in the archive. All right, so here is the basic scenario, right? First, if you do like a textbook on homogenization, right? Typical medium is a periodic, right? Initially, there are no small parameters. There is, that's how I explained to physicists, periodicity, right? Measured in what? In meters, in inches in this country, right? Then there a two-phase medium, a matrix and inclusion, right? So if you mechanics guy, then this is a heterogeneous Helmholtz equation, right? frequency, this is a density, and this is stiffness, right? Both of them allow two different values, right? Two constants, positive for stiffness in the matrix and inclusion for density. So they, as the functions of x, they are periodic with this period L. And then you introduce a small parameter, the only one, is a contrast. You assume that the inclusions are much softer than the matrix, right? They're kind of gelish things, right? Gelish things. And the ratio of the two, A, is a small parameter, delta, right? Soft inclusion versus stiff matrix. For simplicity, that could also be generalized, let density be comparable or just equal. Then if you try to, because of the high contrast, and this is a key point why you have a kind of homogenization still half relevant, right? Because of the high contrast, for a preselected frequency, right? If you selected a frequency and try to propagate waves in inclusion, in matrix without inclusions, or in inclusions without matrix, separately into uniform medium, then the same frequency that generates high contrast in the wavelength, right? The one in the inclusion is much smaller than the matrix, and it is scaled to the square root of the ratio of the stiffnesses, square root of deltas, right? And then you say that the other assumption is that we are interested in frequencies comparable with eigenfrequencies of those gelish things, right? Instead of soft things, like my naive intuition says that there will be low frequencies, right? Resonant frequencies, they will appear low for the outside observer. Right, and this leads naturally, I think that's all I explained it, physically minded audience, right? Kind of scaling analysis. And you want to take the kind of, to say that we are in this resonant regime is the same as to say that the inclusion wavelength is comparable to inclusion size, that is comparable to the periodicity size, right? We don't do, there will be other modifications with modifying, altering the size of the inclusions, and then kind of the larger of the length scale is the macro scale, right? The ratio of the two epsilon and other dimensional parameter in homogenization is the same as the ratio of the wavelength, therefore it is contrast squared, right? It's kind of scale analysis explanation why there is a critical scaling, right? All my poetistic skills here, right? What I have just said, right? The say frequency generates kind of the wavelength comparable with the size of the inclusion, or resonance scaling, in other words. But on the other hand, if you are a guy living in the matrix, this is still long wavelength regime, which means that you hope that you will be able to keep homogenization, because classical homogenization is about the long wavelength regime, right, in the dynamic context. So this is half classical, right? And now, if this suggests after do this all this kind of non-dimensionalization, it's kind of typical scenario, right? The coefficient is unity in the matrix, epsilon squared in the inclusion, periodicity is epsilon, right? This usual way highlighting it. So, right, and this is a mathematically, this is a spectral problem, right, for operator with periodic coefficient, right, about the behavior of Lockyer-Bloch spectrum when there's only small parameter, epsilon, square root of delta, tends to 0. And that's people who do two-scale expansions, they know how. Always, if you don't know what to do in the integrate by parts, so do this, right? Plug this two-scale ansatz and start turning the handle in equating the coefficients, right? And if you do this, and you see I highlighted in red, normally if there were no high contrast, then in the first step, you observe that the leading order term does not depend on the microscopic variable. We need to do 2 more steps, so-called cell problem, and then end up with homogenized equation, which is just the same class but with constant coefficients. Here it is not anymore true, or better to say it is half true, since this is the leading order term is still like in a classical case in the stiff matrix. It is still no fast or microscopic dependence, but that's not anymore the case in the inclusions, and instead of, like it's written in terms of a spectral problem, if I did classical homogenization, I would have, there will be only upper line homogenized equation, but here I have a coupled system, right, between, for this U0 bit in the matrix, and there is an extra guy. If you chipped off U0, there will be this V function which lives on the inclusion only, and it is bounded for on the inclusions boundary, and this is the coupled system, right? And this is another manifestation of this critical scaling, right? These guys contribute simultaneously at main order. They are coupled, and this is and the coupling is, you can see by naked eye how the resonant effect, right, appears in the coupling. The lower line is inclusion problem you need to solve with certain x and y are deemed independent variables. This can be regarded as a forcing, and it looks like if lambda is close to the eigenfrequency, the Dirichlet eigenvalues on a single inclusion, everything blows up, right? And that's exactly what happens, and you can control the effect of all this. People did it before. Zhikov, among other, I think he did it all honestly, right? So essentially, you can do this formal decoupling procedure starting from the lower line. So this is just a constant because that's equation for y. Take it out, and you have a. So I guess it's consistent with the intuition, right? It's like exterior forcing is almost like shaking it with a kind of in a coherent way, and then of course you have to be away from the eigenfrequencies because otherwise everything blows up. And doing this formal calculation, you can uncouple. Uncouple this system and end up with equation for U0 only, right? You can eliminate V, and this is what Zhikov did. And instead of, you have this kind of equation for U0 uncoupled, it has a nonlinear and sign change independence on the spectral parameter beta, right? If beta can be positive or negative, and switching occurs exactly at the resonances, right? You can see the moral is that you can see by naked eye how the kind of the effect of this small resonators on switching between bands and gaps, right? Incidentally, I skipped it. There's interpretation in terms of so-called electrostatic problem, right? On the other here, again, resonances, eigenfrequency, and kind of another spectral problem. Yeah, so that's all kind of formal. First, second, it's just a basic model, and this is self-advertising, but also emphasizing the fact that the underlying effects allow of a more general nature, right? You can consider various scenarios, actually starting from our collaboration with Zhikov and my then PhD student Kirill Chernichenko. So it allows to pick up other interesting effects, not only band gaps, like spatial non-locality for if you are allowing not only high contrast but also high anisotropy, you can allow high contrast in density, some more interesting effects. Papers with Natalia Babic, and so there are some other effects. So I need to sit down and try to refresh my memory on this, because as far as I could see, including last year in this program, that of interest to various scenarios and whether you can pick up Willis-type coupling. It looks like you can on that way there will be what some people call us ourselves, including directional localization together with frequency, and they're often coupled in a more mysterious way. And then you can consider it from a more kind of more general mathematical perspective. We had a paper with Ilya, actually in memorial issue for Zhikov, who sadly passed away years ago. Yes, I think here was actually some defects, like localized modes due to defects. So I guess you can play with that in other Timoshenko type lattices. There are some fundamentally some effects, but interesting modifications in various kind of whole bunch of interesting effects, which justifies the effort on studying it from more general, this kind of class of problems from more general mathematical perspective, right? And this is essentially what we tried doing, following some ideas of Zhikov. So if you want to do it honestly, you have to go into depths of the spectral theory, right? And the initial operator with the epsilon periodic coefficients, back to that basic model, right? Epsilon periodic operator, it is self-adjoint. It's part of Floquet-Bloch theory, but has to be rescaled if you want to do its asymptotic analysis. What you do as that formal calculation, and Zhikov recognized it, in fact, that describes that coupled system, right? Let me show it. Oh, yeah, not immediately obvious. This is just a result of turning the handle, right, of a two-scale expansion. But the left-hand side actually defines perfectly legitimate self-adjoint operator, but in a bigger space. And this is a source of mathematical challenges, right? The limit guy is, in fact, a self-adjoint operator, but in a double space, right? Functions of two-scale functions of x and y. So this guy is L2 in physical space where we live, and this is a subspace of the two-scale physical space of functions of x and y. In fact, those which are subspace, because y dependence is restricted to the inclusions only, and people know in spectral theory it's linear form, right? Eugen Shargorodsky pronounced this spots, right? Early in the program, so that you need to define self-adjoint operator, you need to specify SSQ linear form, right? That's classical, and here is its two-scale version, right? So functions of x and y only, so gradient and kind of x gradient of this u guy, and v depends on y gradients, right? This as a self-adjoint operator, it has its spectrum, and its spectrum is exactly at what Zhikov also showed, right? Non-negative self-adjoint operator, spectrum is non-negative, and it is over a band gap, still over band gap structure, even if it is not no explicit periodicity anymore, right? And it is precisely where this beta switches signs, it is precisely where the gaps occur for intrinsically for this self-adjoint operator. But the key question is how to connect this, rigorously control the error of the approximation, and this is really a challenge, right? Have to be quick here, but maybe I'll give you a taste. What Zhikov did connection in terms of convergence, and that's already tricky enough, but no information on rate, because that appeals to the language of so-called two-scale convergence, right? We don't want to stop this big industry on its own. The point is, it's not enough for us, right? Because it's essentially you need to make sense of the fact that you have a function u epsilon depends on x only, but the limit is now a function of x and y, right? How you make sense of this, right? Especially if you need to, that technicality is better to skip. But there is a method to do it, allowing starting from oscillatory test functions and defining weak to scale convergence. There's some duality arguments. Well, let's skip that, and this allows to say something about the convergence, but no information about rates. Couldn't be. To do rates, you need to go back to basics. Essentially, for the convergence, by the way, the key lies in analysis of this resolvent problem, right? You need to step on the left to consider what? Heterogeneous Helmholtz equation with the wrong sign, right? And if you are able to pass through the limit and control the error of the approximation, then you can, there is a machinery to translate it all to what convergence, spectral convergence is, you wish. That was done without rates, and to do it with rates, you need to start with this resolvent problem, and try to approximate it in an intelligent way, right? What you do, first, it is epsilon periodic. Step one, okay, technicalities, not important, I guess, for a weak formulation of variational minimization problem, restated if you prefer. You do rescaling, right? Scaling operator, in fact, right? It's a nice operator, right? So you need to stay on the, you better not to restrict yourself to operators and better to unitary operators, so at least to this non-preserving isometric, right? So scaling is isometric operator. Then you do next step two, Floquet-Bloch-Gelfand transform, right? Here in this audience, that's pretty well-known creature, right? It's modification of Fourier transform for essentially for representing any function as a superposition of quasi-periodic functions, right? This is my rescaled solution, sort rescaled solution. I do Floquet-Bloch transform and decompose it into integral over the duality cell, Brillouin and so on, quasi-periodic functions, isolating this exponential, and this guy has to be periodic, right? And for this guy, you end up with equivalent problem, right? Everything is equivalent, you need to be able to come back, right? Nothing lost. You have the problem falls into a family, right, of this quasi-momentum theta, denoted parametrized rescaled problems. Then you need to pass to the limit in a uniform manner, right, with respect to theta. And if you look carefully, because of this high contrast, there is a high degeneracy, right? And this is the source of these two things, right? There is epsilon minus squared, and there is a form A theta, which is uniformly positive only on the matrix, but degenerates on the inclusion, right? And B, we call singular, regular, right? Singular perturbation problem. You can say, and then you do what? Much depends on the kind of a null space, right? The general space of this where you live, that singular form degenerates, but it depends on theta, non-uniformly, right? If theta is 0, it's periodic case. Constants are allowed, but then anything is allowed in the inclusion, right? And if theta is not 0, sudden jump, right? A lot happens in a small neighborhood of this theta equals 0, and you need to be do very careful asymptotic analysis. Again, I will probably skip the detail here, and then you approximate the singular form to in a controllable manner by kind of homogenized form. It's actually for perforated domain homogenization, but there is this regular form remains in the game, right? And but you have this both two guys. It's a kind of rescaled, transformed version of this two-scale limit problem. And there are some other important detail to control the degeneracies remaining in the limit problem. And then you do inverse not Floquet-Bloch, but Fourier, because there is some self-similarity. Maybe another naive intuition, I explained to myself. Scaled Floquet-Bloch transform is on epsilon periodic cell. The dual cell, like physical cell shrinks, dual cell expands, right? In the epsilon minus 1 pi. When epsilon goes to 0, the dual cell kind of expands to infinity. and you lose periodicity, and then you need to do Fourier inverse transform, but inverse is not Fourier rather than Floquet-Bloch. And this is a kind of result with implications that you succeed, right? You control it in the best possible in operator form sense, and then you have these two scale limit operators stuck inside, but you need to connect the two walls, right? You need a device. You need a device for like started from the right hand side actually, right? You give me any function, and I want to construct approximation uniformly valid for all the right hand sides f, including those which invisibly oscillates effectively of this, and I need an operator with an I for interpolator, which kind of produces from single scale function a double scale function, right? And this is achieved by this mysterious combination, like the sum against some detail, not everything at once. There's another important object, a translation operator. Well, this is a kind of universal guy, naturally pops out here. We have called it two-scale interpolation operator, right? And this achieves exactly that goal, right? I have to wrap it up. Yeah, B Bloch transform, right? Floquet-Bloch. This is gamma scaling. Everything is L2 unitary, right? Because you need to control the spectrum. And not allowed step to the left to step to the right. You will lose everything. Scaling transformation, right? Normalized L2 unitary. Floquet-Bloch is L2 unitary, right? From R2 into the product of the dual periodicity cell and the dual cell, right? L2 unitary. Then you have to this intuition blowing up thing. You need to extend it to zero, but it is a controllably negligible, right? And the extension operator is not unitary but isometry, right? Still. And then you do inverse Fourier transform. And after you've done it all, okay, it's nice operator structure, a lot of combination of various transforms. You do explicit calculation and see, look, where did I see this? I saw it when my son was struggling with the electric engineering signal processing course, right? This is the keywords is kind of different world. Not sure how many people would know about this. I didn't. From 100+ years old story in signal processing, so-called Shannon Nyquist sampling theorem. We take a Shannon interpolation operators. Essentially, key role is played by this sync thing, and this guy achieves the goal, right? You sample you give me a function. I want to represent it as a function of two variables, right? I only sample points which have a given phase y, and then I read off the values there, and then I interpolate in between, interpolate in a smart way, infinitely smooth, and in fact, real analytic, right? Sync function, right? Is where is that? Yes, sync, right? Is sine z over z, right? Kind of discrete delta function. So it allows, again, Simalto is already reminded to me, so that's okay. So this allows to essentially, for the spectral part, to prove the theorem, right? Not only one spectrum converges to the other, the difference between them is controllably small, right? To say something about the Bloch waves, and so on and so on. I can talk about that forever, of course. So that's actually interesting thing that it has some nice properties, right? Producing function of two variables from function of one variable, and this has, if your function is differentiable, right? Then it applying it to gradient, you make it to scale a chain rule. So this formal two-scale asymptotics becomes rigorous in a sense, right? If you apply this thing, because you're staying on this equivalent reformulations, back and forth. You can always return forth. Of course, there is no free lunch. Yes, okay, and I didn't have a chance to say that. As I said, that in reality, it's kind of very few basic principles there, and you can no extra effort, not much extra effort. You can do it in some generality, means that they expand the abstract form, and as a result of that, to get actually it's an incomplete list of examples. You know, it doesn't have to be matrix inclusion, doesn't have to be PDE, could be discrete system and so on, and some strange terms, imperfect interfaces, concentrated masses, and so on. Details are available. Sorry, I overrun it.
No,
thank you.
Okay, thank you very much. For the coffee break, was there one quick question? Just one very quick one from me. So you have in your setup, there was perfect bonding between the matrix and the particles, and that ended up with a cell problem that had a Dirichlet eigenvalue problem. Are there generalizations on that if you have other boundary conditions?
In fact, that's highlighted here. The imperfect interface, right, is one of the scenarios. That's exactly, yes, my intuition, probably yours as well. Instead of this jellyish stuff things, I can have soft debonding, right?
Yes,
Soft springs, right? And if again scaling is, and this is example number 5 in our preprint, maybe 6, I can swear, right? I haven't gone that far yet. And that's actually there will be in scalar model, there will be single resonance, right? For in elasticity will be what? 2 or 3, right, depending on your dimension. But conceptually the same thing. Again, there are some subtle details and interesting modifications, and this is highlighted. The abstract scheme doesn't care about the details. Kind of the core of it remains. Yeah.
Right. Well, thank you very much again. And actually, thanks all.